Is the screen visible? Okay, good. So let us start with a very quick summary of the last class. That we started off dealing with the details about how partial from the partial data that is given, how can we learn a conditional probability distribution table in Bayesian net. We saw there are two problems. One may be the joint probability distribution. If it is fully given, we have no problem because I can just refer to the joint probability distribution and get any value. If we are given this Bayesian net fully and all the conditional probability distributions tables at every node, then also we are done because this Bayesian net automatically derives a formula, and from the conditional probability distribution we get it. But the situation becomes complicated when the Bayesian net is fully known and data is fully observed, but not the full joint distribution table is in your hand. And you also do not have a complete view of every node's conditional probability distribution table. Then our old methodology of maximum likelihood estimation rescues us, and we just take that table, sum over all of them where some of these values are satisfied, divided by the sum according to Bayes' theorem, which is there in the denominator, is these two values are satisfied. Now also we moved on to seeing that if the Bayesian network is known but the data is partially observable, remember in both these cases the joint probability distribution table still is not fully given. But in the first case, whatever is given has been fully provided. In the second case, whatever is given in the joint probability distribution is partially provided. That means there are some entries which are kind of don't know. So in that case, we need to fix those entries first and then need to go for maximizing our probability estimation. So kind of fixing those entries is an expectation step where the unobserved variables, we try to expect a value which is 1, 0 or whatever level they wish with respect to the predefined theta to start with, and then at each iteration that theta will be supplied after m step. With respect to observed variables, we want to see whether when z equal to 1, what is the expected value of that when z equal to 0. And depending on that, we again try to compute the log likelihood and try to take the max argmax of that, which maximizes that log likelihood, expected log likelihood. And in this way, we iterate upon this, and we have seen that we come into a global, I mean, we cannot reach always a global maximum, but we sometimes do a very good job and find a local maximum, which is many a times a global maximum. And this converges after a few iterations, and we call this as an expectation maximization. Expectation with respect to providing the unobserved data and expecting a value from it. Depending on that, we maximize and iterate over. And we have seen that an implication of this in the Bayesian classifier. All of these methods also rely on the maximum likelihood estimation, because ultimately at the end of the day, we have only a partial joint distribution table. We need to only compute depending on the number of entries that is being satisfied, and we need to predict depending on whatever being satisfied, and we just predict or learn that CPD. We have seen this is a very special case of unsupervised learning as well, because in clustering, for all the rows, if you just omit the output rows everywhere, make it as a partially observable where you cannot observe the output level, then the same problem, you can figure out that this problem is again a unsupervised learning or a clustering problem, where you only have the attribute values but not the outcomes. So then the learning using this expectation maximization converges into the similar clustering sort of form. And you can, if you do that, you will see you will get a similar kind of a performance just you did in hierarchical clustering or K-means partitional clustering. We have also seen sometimes not all the points are drawn from a particular distribution, but it may so happen a point somewhere may be drawn from a different distribution. And if we need to cluster or if we need to classify, we need to figure out which distributions they belong. For that, again, our Bayes analogy of probabilistic notions help, because I will assume that its distribution is generated by ith Gaussian, and then depending on that assumption, I will generate the distribution and try to maximize the expectation of ith Gaussian generating that. So again, that's an application of expectation maximization procedure, and we iterate over it. It's a hairy mathematics. I did not put it here, but ultimately what you get is this in terms of the priors, and you also can maximize with respect to the means, mu gi's for each Gaussian, and the computation is there in the slide. You can refer to it, but this type of applied area in expectation maximization is called the clustering or classification using Gaussian mixture models. And this is one of the applications where Gaussian mixture models are being used. Today, we will see another applications where we extend the notions of Gaussian mixture models. So let us start with the today's proceedings. So sometimes in many practical situations, we often encounter that we see observed outcomes, but we do not see the player's internal behavior. For example, let's say that you see, suppose a robot is moving and doing something. What you see here is that I see that at step 1, what are the outputs? At step 2, what are the outputs? At step 3, what are the outputs? At step 4, what are the outputs? Robot is moving in its way. Okay, but you can only see through the observations of the outputs that is found from the robot's activity. So these are observations. What you cannot see is the internal state of the robot, right? Robot is moving from Y1 state to Y2 state. In Y1 state, it produces this outcome. In Y2 state, it produces this outcome. In Y3 state, it produces this outcome. In Y4 state, it produces this outcome, and so on. So therefore, you can see that there are certain observations you want to make, and obviously your question is that you should reason about the behavior of a robot in terms of probabilistic sense as well. So these things are known as the states of the player, and often we see that these are hidden from us because we do not know whether robot is doing by, I mean, its own state is a very complicated combinations of its internal state variables, how it is designed and how it is learning the scenario. However, we have only clues about certain outcomes that it produces and certain probability values of these outcomes which we may gather depending on a simulation run of the overall robot doing something in a scenario. So such kind of model is often called, since this is hidden amount of state information is there, such kind of model in machine learning parlance is called as hidden Markov models. Now, I have explained to you why it is called hidden, because the internal state is not observable, only the outcome is observable. I will also explain why this is a Markov model. First of all, let us try to blow up a particular position. So there is an internal state, it produces an outcome. Right? This is our model, and we proceed on. Now, obviously, internally somewhere, unknowingly to us, this y is a distribution. So there is a probability of a robot being in state y. So this y, that means this y could be some value of y1, it could be some value of y2. So it may follow a distribution, and usually it's a multinomial distribution which we observe in practical scenario. It's a multinomial distribution which we observe or take for mathematical analysis, and we observe in practical scenarios. Also, since I get an output considering I am in a state, therefore I get some x given some y. This also follows a Gaussian distribution. The reason being this to be as a Gaussian distribution is that I am assuming the outcome behavior is continuous. If I assume outcome behavior to be discrete, then it also is a multinomial distribution. Okay, because multinomial distribution is, as you can understand, it's due to it happens. I mean, it is used mainly due to represent discrete states, whereas I use Gaussian distributions to represent continuous state. So these are 1-2 assumptions that we make in order to mathematically formulate. Now, why we call this as a Markov model is the fact that Whenever I am in a state, I only am dependent from where I came in. I do not want to remember all my past histories to dictate the behavior in this state. That's why you see there is only one arrow to x2 here, because given this state, I can derive an observation from here. And this state is only dependent on the previous state. There are no arrows following from the past states. Even the observation is not directed from any of the past states. Therefore, there is a process which we call as a Markov process, which is the inherent assumption on this model, which says that the probability that given I am in state t plus 1, given that I pass through the state t minus 1 from 1, is equal to the probability that my probability of I having yt plus 1 some value, given that it is only yt. I do not care about these dependencies. So yt plus 1 is conditionally independent of yt minus 1 up to y1 given yt. Only thing that matters for yt1, what is its previous state? And that's the assumption in the Markovian process we make. And we take this kind of hidden Markov model under such assumptions. So now let us try to move a little bit further about our discussion. So there are certain kind of stationary processes here happening. One is this Markovian process, which dictates the next state with respect to the present state. And it always has a probability value which is only dependent on the previous state. There are something called initial distribution, which is that what is the priors? What is the prior probabilities of the state? That it is irrespective of anything. I am just computing the priors, and obviously we take as we have done here, we take the priors as multinomial. It's a discrete state value prior, so we can take multinomial distribution for that. There is something transitions here, transition in this with respect to the states from one state to another. Sorry, from one state to another, I keep on transiting. So that is the transition distribution. So which is the probability of yt given yt minus 1. So for every t, y2 given y1, y3 given y2, this distribution is given. Since it's a discrete movement of state, again, this is, we assume, as a multinomial distribution. The third thing is the emission distribution. These are the terms that is being used. I mean, if you do not remember these terms, absolutely okay. You need to know initial means the priors. I need for my analysis some kind of Markovian process to follow. So I need a transition of the state distribution, and there is an emission. You could think this as an emission, that in each state I emit an output observation. So obviously this is x t given yt. And for this, I assume in the hidden Markov model, there are two things possible. One is it could be a Gaussian, depending on the scenario that we are observing is a continuous scenario, or it could be a multinomial distribution, depending on it's a discrete scenario. Remember that you do not have to freeze these distributions ahead. I am just freezing it in order to make my analysis going and try to making it more close to something realizable. In practice, this Gaussian multinomial distributions can be something else, but the point is that I should have these informations in my computation, and I am just assuming certain distributions to make it more realistic. That's the whole thing. But you need to have initial distribution, transition distribution, and emission distribution. And depending on these three, my hidden Markov model is defined, because I need to define this state space perfectly, right? Depending on these three, my hidden Markov model is actually defined. Agreed? Any questions till now?
Sir, initial distribution, please repeat.
Initial distributions means it's the prior. So prior, what does it mean? Suppose the robot does three things. It eats, it plays, it sleeps. So what is the prior, that what is the probability that yt equal to sleep happens? Or rather, you may take it in a realistic way, though a little bit a loose way, that what is the fraction of time in the day that robot sleeps? That's a prior information, right? That's the initial thing.
Okay.
Transition says that if robot sleeps, upon waking up, does he play? If robot sleeps, upon waking up, does he eat? These are all transition probability. Emission probability, while sleeping, what do you observe? You observe the snores, you observe any beeps. What is the probability of that given he is sleeping? You observe the snore, what is the probability of that given he is playing? He or she is playing, like that. These are your emission things. Any other questions? So why I covered it just after the Gaussian mixture model, as you can see, now you need to reason about kind of a joint distribution of the states, observations, and try to figure out whether something will happen or not. For example, I may question that what is the probability of y from 1 to t and x from 1 to t, all these variables. So this is nothing but, as you can understand, I want a joint probability distribution table. So in this joint probability distribution table, there are different kind of distribution being merged, right? So it's a mixture of models, because to explain this, I need help of all these values. Agreed? If these are distribution, so it's a mixture. If they are distributions having some Gaussian, it's a mixture of Gaussian models. Yes, agreed?
Yes, sir.
So depending on that, let us try to just derive the initial step. How do I go about doing this if my y1 to y2 are related in this way and I know that these are in my hand? So the probability of y1 to t, x1 to t, this means it's a combination of y1 comma y2 comma y3 up to yt and x1 comma x2 comma x3 up to xt. This is nothing but, you can say, it's probability prior of y1, then prior of the next all states given the previous states. And since there is a conditional independence, then I can do this for I equal to 1 to t minus 1. And then again, I have the observation variables also, which is conditionally dependent only on y1. So the observation variables, I will do xi dependent on yi. Then my I here is equal to 1 to t. Right? So to compute the joint probability distribution of this thing, I need to know this prior, I need to know this, I need to know this. Then by iterative or recursive way, you can just go on computing these values. Right?
Yes, sir.
Let us try to more dig it down. So this is a very naive way of saying that what I will do. Not always I need the full joint distribution thing sometimes. But what I need, if you look closely, what are the activities that I need out from here is that one thing I need to monitor what the robot will do, or maybe some of the system that we will do after certain steps. So if I know the observations from x1 to xt, what it will do at xt plus 1. What it will do at what is its state at yt plus 1. Sorry. So what I'm saying that I know I have seen the observation of the robot from x1 to xt. Can I predict what will be the next state at t plus 1? That's what is the immediate monitoring. What else I can do from such a model is I could predict. Right? How I could predict that suppose I know from x1 to xt, can I say how the weather will look like at t plus k, where k is strictly more than 1? That's a prediction because I only have the observation up to this point, but I want to predict something very far away. From this model, I can also look some hindsights. I will give you example where it is used. Hindsight means you observed many things. Now you want to predict some state intermediate of it. So I observed x1 from to xt. I want to predict a state which is k less than t, intermediate somewhere. So all these activities I can easily do if I have this model, and I can have algorithms for each of them to be very specific and doing it very meticulously. Let us see one by one. By the way, any questions in understanding that what we are going to reach here, derive here?
Excuse me, sir. Sir, are there certain set of activities that the robot can do, or it is infinite?
No, the actions of the robot are finite. The actions
and
of
the
the
states
robot,
as well.
absolutely. Since if the actions of the robot are finite, therefore the internal states of the robot will also be finite. However, there are cases where we also can do it in infinite way, but see, I mean infinite in a sense that we can predict up to a finite future, right? So you cannot say that infinite many days afterwards what will be the weather. That you I mean you are least bothered to predict that. So all the activities over this in monitoring, prediction, looking back and checking the states and all have certain purpose. I will give you examples for that. But according to your question, the answer is yes. Under a finite set of actions, under a finite set of state exploration, we are trying to tell something.
Okay, sir. Thank you.
So let us start by monitoring. Just I will use Bayes theorem and conditional dependence and all that. What does monitoring say? I want to predict what is the probability of tth state to be some value. So this yt by me, I am meaning yt equal to a, yt equal to b, something, which values that state can take. Given that I have observed all my outcomes up to t. If I have observed all my outcomes up to t, I want to predict what is the state at tth point. According to Bayes theorem, you can easily see this can be modeled as a probability of xt given. So I am just using Bayes theorem. So this means x1 comma x2 up to xt. So this is xt given yt comma x1 up to t minus 1 into probability of yt given x1 to t minus 1. So this is just in the first step I use this is the Bayes theorem, nothing else. Now in the second step, you can see that this thing, when I look into this thing, my xt is conditionally independent of x1 to xt minus 1 given yt, because just look at these, that this is y1 giving rise to x1, y2 giving rise to x2, y3 giving rise to x3, y4 has given rise to x4. Now x1 and x2 are conditionally independent given y1. Similarly, x1 and x3 are conditionally independent given y1, the d-separation algorithm that we discussed. So this will give me probability of xt given yt, because rest I can ignore as they are conditionally independent. This, what I want to do, I want to go one step back and try to calculate the marginals of this with respect to the probability given x1 to t minus 1. Why I am doing this will be clear after I derive somewhere. So what I did here is that all possible values of yt I can sum up, then this will result. So effectively you can see that to have this equation going, I can easily do it by this way. Right? all the marginals of yt, I can sum up, it will get this because there is nothing here. And this part has been provided as conditionally independent with in this. So to write here, this is due to conditional independence, and this is due to the marginal contributions. Now the first term, keep it as it is. The second term, if you look carefully, so the second term, now I can write it as probability of yt given yt minus 1 x1 to t minus 1, just applying the chain rule, nothing else, the chain rule here, into probability of yt minus 1 given x1 to t minus 1. This is the chain rule. This and this and this, given that this one is this, given that everything, into this, given that the rest of the thing. This is nothing but chain rule. Now you somehow predict that what I want to do now, because you see this is a recursive term that I get considering this one where I started off. So therefore, this thing, suppose I tell it this as let's say this is monitoring, I call it as MT, then obviously this one is probability of xt given yt summation of all the marginals of t minus 1, probability of, sorry, this is yt given yt minus 1. Now see here, yt is conditionally independent of all the x's given yt minus 1, because this is only dependent on this. This is conditionally independent of all the x's. So I can write it this way. This term is m t minus 1. Right? So what does this analysis derive us? This analysis derive us, I can recursively solve it first of all, because I know this probability. I know this probability because this is, one is my transition, one is my emission probability given to me. I can solve this one recursively. What does recursive process will do? Recursive process means that first, what you do, you first try to go with the prior of this one. So recursive process proceeds in this way: prior of this one into this one. Then these two compute this one. Also get a hold of these two as well. You need this probability as well. Then to compute y3, you go with this 3 into a probability hold of this thing, which essentially becomes with this 2. Right? Because this doesn't matter. Similarly, you move on. Let me just remove the cluttering. So you move on like this. In the third iteration, you move on by computing this. In the fourth iteration, you move on by computing this. Recursively, what happens? You start in the back time. When you hit upon a base case, you come with the prior and this, you go on computing this. Finally, your recursive steps moves on like this, computes the final solution bottom up. Okay, got it? This is what the monitoring strategy is.
Yes, sir.
So this is also the algorithm that we give is also known as forward algo. As you can see, we call it a forward algo because I can do it in one pass. I am calling it recursively to explode the tree, and then reaching the base, I go forward. But the computation goes in one pass. Prior of this into probability multiplication of this one, then probability of this one multiplied again, and probability of this one multiplied again, get up to y2, then up to y3, then up to y4. It's a forward pass that we are making, and that's why the algorithm is called a forward algorithm. The thing that we discussed is called a forward algorithm in the monitoring. So where does monitoring helps? Monitoring helps sometimes in Alexa. In Alexa, how do you record your voice so that a future thing, it could predict some syllable, you are telling it in this manner. So some system which the state to be identified from the past history, this monitoring of hidden Markov model is very much apt for it. For example, in case of sound or audio recognition, in case of robot motion planning, so each step you plan. So in all these cases, this monitoring helps. Let us go to the second part, prediction. And as you can see, the prediction, you can easily understand where does it help, because it helps kind of a agent to predict the weather, sunny or rainy something, much ahead upon the observations that is being given to him. So therefore, the prediction of this one is again the probability that I want to ask for is t plus k, given that I have observed from x1 up to xt, where k is strictly greater than t. So again, let me formulate the recursive solutions and then we can derive the algorithm. So here what I will do, see it's a t plus k. So immediately I try to bring in the marginal factor of it. T plus k, y t k minus 1, given that x1 to t with respect to all y t plus k minus 1. So this is nothing but this is the theory of marginals. Then let us proceed. Then what we do, we apply the chain rule, because this will be this, given that yt k plus 1 and all that. So summation yt plus k minus 1, probability of yt plus k, given that yt plus k minus 1 and the other things, into probability of yt plus k minus 1, given that x1 up to t. This is nothing but application of chain rule. Now I hope you can understand where we are moving on. So this is conditionally independent of everything else except ytk plus k minus 1, this one. So this is yt plus k minus 1, probability of yt plus k, given that yt plus k minus 1. Now this, as you can see, I have already got kind of a recursion with respect to the k values, right? So where I need to reach it up to, I need to reach this up to k minus 1 until and unless k equal to 0. Then if k equals to 0, my monitoring will give me the direct answer. So here, as you can see, I started off with prediction, so pk, and I got here pk minus 1. Agreed?
Yes, sir.
So if you now try to rethink how this recursion proceeds with our algorithm, I have y1 observation x1, y2 observation x2, y3 observation x3, y4 observation x4. Now what I want to do, I only have a view of this. I want to predict this one, right? System will move, but you only have a view of till this point. Not the hidden state, but only a vicinity of this. So what I will do by this nature is that you would like to compute till this point, right? This k minus 1, I will come back to see this one. Once you do that, getting y2 from x1, x2 is your monitoring. The monitoring will directly give you the answer, right? Getting yt, given that x1 up to xt, is direct monitoring. So essentially, direct monitoring, as you know, it's a forward chain rule. So you just compute this by monitoring, and then suddenly this algorithm of recursively calling back will keep this value, but try to predict this one. Keep this value, try to predict this one, which means it only uses this prior probability, this one, to dictate the previous probability value and move on, right? Even if this is also a forward algorithm, because though we formulate recursively, but we stop observing at a point and then move on forward depending on the previous state at our hand. That's it. We do not have any more observations to support, because if we had that, it is nothing but monitoring. We can monitor up to certain point, but need to predict the state from the previous state combinations that we have. Given that state combination, what will be the next state is our prediction. So this is also another forward algorithm pass that we'll do. Clear?
Yes.
See, what I am not doing is that I am not writing the algorithm. These all algorithms are one of the contributions in hidden Markov model. Rather, I am just formulating the problem in such a way that you yourself can write the algorithm. So once you see that these are available to me, tk with k minus 1, I have a recursive formulation. If k reaches to 0, then immediately I will invoke the monitoring factor and I will get everything. That's the algorithm, nothing else. The third thing that we already talked is the hindsight. Sometimes these are required to know the states. Many a times in audio learning, audio data like speech recognition. Why it happens? Suppose I have y1, it dictates my observation x1. Then it goes to y2 state, I only can see x2. Then it moves to y3 state, then it moves to y4 state, I can see x3 and x4. So now see, I have seen all this. I have seen x1, x2, x3, x4. Now I need, after a certain observations, I found out that I need to know this state to further classify something, recognize something. Just it is connecting the dots between your speech. So I need to see some hindsight. So for that, obviously our formulation is I need to get this probability of, sorry, this is k given x1 up to xt, where strictly k is less than t. That is my hindsight problem. Now, in order to get that again, let us try to formulate. So this, what I will do is this one equal to, I will write probability of yk, then y k plus 1 up to t given x1 up to k. So why can I make that? Can you tell me why can I make that? Can you tell me, can anybody tell me why can I make it k? Just think, this conditional independence follows that. See what you are predicting, this one, right? This one given up to t doesn't matter the prediction of this one, first of all, right? Yes or no?
Yes, yes.
You are not thinking. I will not tell. I leave it to you. If you do not find, then just mail me. Just think why this is k. So if you could do that, then what I will do is the same chain rule I will apply. So this is application of chain rule. Then what I will do that now you can see that it is x k yk given x1 to k, this one is my monitoring, right? This is the monitoring part. This is the monitoring of k. This one I need to derive. So let me derive the other part, which is probability of y k plus 1 up to t given x1 up to t. To derive this one, I will first do a marginalization, which means I will sum it over with y k plus 1. This is probability of y k plus 1, comma, just a minute, what I did here. sorry, just a minute. I'm sorry, I made a mistake here. This is the case. I'm very sorry. I made a mistake here. Let me come again. I hope that's why you cannot predict that what I am saying. I'm sorry. So what I did here is that, see, due to this is 1 to t, and due to the conditional independence of yk with respect to the future ones beyond k, I can write it this way, right? Yk, and the from k plus 1 to t I can put it here, and up to k I can do it here. This is the conditional independence that I have derived. Now, once I do that, then immediately it will give me rise through the chain rule that probability of yk given x1 k into probability of xk plus 1 up to t given yk. Right? Agreed?
Agreed, sir.
Sir, second step, like y x k plus 1 to t.
No, the thing is that, see, from here to here is just the conditional independence. Yk is dependent from x1 up to xk. Sorry, I mean, I'm saying that yk is only dependent upon x1 to xk, not xk plus 1 to t. Right? So if you write this, if you write this probability of yk given x1 up to k, then k plus 1 up to t, then this will be probability of, see, yk is only dependent up to this point. The rest of the point yk is independent of. If yk is independent of that, you can put in all this factor here, given that you may say, suppose this is my star, given you can say this one through conditional independence. Yk is conditionally independent of star part given x1 to xk. I can just write this.
Okay, sir.
Okay, so that then it follows. I mean, I just made a mistake here. Please note that. I mean, then it automatically follows, because this is what we do by chain rule. And you know what I will do next. I will just, this one is my monitoring part. I already have computed this monitoring part up to k. This part I will compute, which is basically probability of x k plus 1 to t given yk, which is computing the marginals yk plus 1, probability of yk plus 1 comma xk plus 1 to t given yk. This is by marginals. Then after that, I will just continue with this probability. I will apply the conditional independence again. Probability of yk plus 1 is conditionally independent of the rest given yk, into probability of yk plus xk plus 1 given yk plus 1 here, into probability of x k plus 2 up to t given yk plus 1. And this is just the chain application of, here I applied conditional independence. I merged two step, and here I applied chain rule. Now you can see where I reached with this. Again, in a recursive formulation. See, in hindsight, what we want to do, I want to see yk with respect to this. I have this formula. This one is monitoring into this formula. This formula says xk plus 1 to t. This formula says xk plus 2 to t when yk plus 1 is there. So if I denote this formula as hindsight of k, this formula would be hindsight of k plus 1. Agreed? So I got a recursive formulation. Okay. Now see, earlier in all of the previous cases, when I got a recursive formulation mt with mt minus 1, pk with or pk minus 1, here I got a formulation where hk plus 1 and here I have hk, which means this algorithm I need to do in two pass, one in the forward pass up to y2 and one in the backward pass from all this again coming back to y2 to get it. Because I observed many things. Those so what is the difference why I did not get a backward pass in the prediction? Because I do not observe anything there. So in prediction, my predicted state will only depend upon the sequence of till how much I observed and got a monitor state, and from that monitor state where can I predict without observation anything in my hand. Here I have the observations. So therefore, these observations will dictate also these state, because these observations are related to this state. I get in y4, that's why I observe x4. So to get here, not only the forward monitoring matters, but also getting these values backward, which brings me here to get this value also matters. So therefore, what we do here in two pass is that we first try to compute y2 given this. So first we go on computing this way. Then we take these two and compute this. And then as we are doing in the forward monitoring. And then multiply everything. So this is the forward monitoring part. This is the forward part. And computing this one is the backward part. Right? So this algorithm of hindsight, we call it as a forward backward algorithm. Any questions till this point?
Sir, move to previous
one, this one. This slide.
Here in prediction part, where k is greater than t. So sir, it should be p y k na, because k is greater than t. So t plus k doesn't make sense.
Why t plus k doesn't make sense?
Because sir, k is greater than t. So we are predicting future.
Yeah, future.
Yes, sir. So t itself is greater than k itself is greater than t. So it should be y.
So what is the problem? The k plus t. What's the problem? I mean, it's not a problem, right? K plus t must be greater than 2t.
Yes,
I'm doing -1 every time.
Yes, sir. Because in the next in the hint side, you did yt only, yk only, because k is less than t there. So to make analogy.
No. You see the point here. I want to predict t up k step forward, right? I want to predict t k step forward. Oh, sorry. Okay. I understand your question. I want to say this is 1. Yeah.
Yes, sir. Yes.
Yeah, I understand your question.
No.
Yeah. I hope you got the essence now.
Yes, sir. Got it.
Yeah. So this.
Sir, I have a question. Sir, in case of forward direction, forward direction, we are going that way because we in our hand the future prediction is not there. But
I mean, the thing is that your recursion will unfold and solve it that way. See, when you calculate factorial n takes the value of factorial n minus 1 to compute, and you unfold it in the opposite way. But when you compute and come back, it's a forward direction from 1 to 2, then 2 to 3. Same thing here.
Yes, and in case of backward direction, all the previous prediction, all the predictions are there. So
yes, all the predictions are there.
Why we use backward prediction?
See,
because
what we did with this marginal in backward prediction is that suppose I have a prediction. What is the chances it is y3 I got this prediction, or y4 I got this prediction, or y2 I got this prediction? I take all possibilities and try to see what will be my previous state depending on the probability of this prediction from every state. To be more precise, your question, I am in a state y. I got something. What this y value is, I do not know, but I know this one. So what is the probability that this value is A? What is the probability that this value is B? Because I have to know this value in order to come back and say what is my previous state. So depending on these observations, I am trying to see if it is A, what is the probability of getting this? If it is B, what is the probability of getting this? And dictate this probability as a marginal sum will dictate the probability of having in this state, the value of
Yes.
this state.
Yes.
That's what is backward.
Yes, I agreed this, but my question is, in case of backward prediction, as per the storing is needed, so that's why the storage complexity will be increased, and that must of things may happen. Na?
Just implement, you will find out. So you can release the storage. You need only this much. So after you compute one, you can release storage and come back.
Oh, acha, acha. Yes, yes, yes.
That's
I
the
got
implementation is. You are more.
Mm-hmm.
You should be more conversant than me.
Yes, yes.
So yeah, this is one of the two algorithms. I mean, mostly it's a recursive algorithms. It's called forward backward because it has an iterative way. We can solve it as it's a probability computation step by step, and we do it in iterative way. However, sometimes also there is another point we want to we want to see is that suppose I go through a series of state from y1 to yt. Given that I have an observation from x1 to xt. I want to see C. I only am seeing these observations. The states are hidden. The sequence of states are hidden. So y1, then y2, then y3. I do not know. These things are not given to me. What I see only x1, x2, x3, and so on. Now I would like to see that what is the most liked explanation? What is the most likely explanation of y passing through these states? Remember, y1 is a value. Let's say the state is a, b, a, c. So what is the most likely explanation that your observation can give about the state sequence being AAC is also of interest. So we call it as a most likely explanation of your output. From your output, what is the most likely explanation that maximizes this observation? It maximizes the likelihood of your observation. So let's say after solving this, I get A, B, A, C is the maximizing of my likelihood that these outcomes correspond to. Get the problem what I am trying to reach here? Yes or no?
No, sir.
No, sir.
You see x1 followed by x2 followed by x3. These are data for you. You do not know what is y1, what is y2, y3. These are hidden. Right? Yes or no?
Yes, sir.
Now, looking at this data, what is the state sequence that is mostly likely as an explanation of this data? So as if you are trying to compute kind of MLE, right? You are looking at the data now trying to compute what is the probability of y1 is A, y2 is B, y3 is A, which is the likely occurrence of the states. Get it? See, I see from the robot is saying first state 011, second state 100, third state 111. Can you say that the robot is sleeping here, here it is eating, here it is doing work and all that? So what is the most likely explanation of these observations? Or the most likely is it is sleeping, then also sleeping, then also sleeping. Among all the combinations, which gives me the highest expected probability value as per MLE estimation of these observations? Now get it?
Yes, sir. Get it.
So this is nothing but as per our previous algorithm, we are just wanting a new thing. We are trying to maximize which valuations of the state gives me higher probability of y1 to t given x1 to t, which is basically what I want to do is that I could just maximize with respect to yt probability of xt given yt into maximize with respect to y from 1 to t minus 1 probability of y1 to t minus 1, just recursively defining the problem. So this we will do exactly as we do forward, backward, and recursive thing. But however, as you see, this is a problem that involves maximization as well. So we will invoke a dynamic programming for that, right? I mean, if there are no maximization, just a forward pass will do it. Agreed or not?
Agreed.
But if there is a maximization, then you need to know about which combinations of them provided you the best likely explanation. So therefore, you know, you need to save some data and need to do dynamic programming in that case. So this is an algorithm which is very famous, which is called Viterbi algorithm. So many of you machine learning enthusiasts, when you start reading it, in your search, this person's name comes up very often. Viterbi. Viterbi algorithm is nothing but trying to make a likely explanation whether this is this or this. The second state is A or B. The third state is A or B. From I do not know anything. I only know that my x1 I got a 0. Let's say x2 I got a 1. So it means that x1 is 0 means I got a probability of x1 equal to 0. I got a probability of x2 equal to 1. So I get these observations from this. So which is the most likely sequence, whether it is AAB or BAB or BBB, which is the most likely sequence that have governed me in this observation. So as you can see, most likely meaning which will maximize the likelihood of my data with respect to the given state sequence, right? So that is what I am doing. Maximize this sequence given to us. Okay.
Yes, sir.
Just one thing that we always see this kind of a thing that y1 then followed by y2 and so on. I observe x1, x2 and so on. But how does this come? Suppose a robot has two states, as I said, it's eat, three states, let's say it's eat, drink and sleep. Suppose when it eat, there is a probability it keeps on eating, let's say 0.1. After eating, it has a higher probability of this, and then it has a sleeping probability of 0.2. So this sum will come to 1. Then again, this it drinks has a probability of 0.2. After drinking, he has a sleeping probability of, let's say, 0.8. While sleeping, it has a very high probability of keeping on sleeping. Then maybe 0.1 here, 0.1 here. From this model, actually, we derive this one. But unknowingly, we do not know what this model is. What we know, at each state, at this drinking state, suppose I have certain variables, x1 and x2, I only can see the probability of x1 given the state is drinking is how much. Probability of x2 given the state is drinking is how much. So this is the hidden Markov model, that you only see this orange color things, not the white color things. So you will only see these and you need to reason. Okay. Any questions till this point? Okay, so that's all I need to cover here for the hidden Markov model. And if you're enthusiastic enough, or in real life, if you face some problems over the hidden Markov models, there could be expectation maximization algorithm also applied. As you can easily see, if these observations are partial, then obviously I need to assume something and then expected value and then try to go on maximizing it. Right? I mean, you guess the point. So what would be partial? The partial would be the priors. The partial can be the transitions. The partial data can also be given with respect to the emissions. So these tables, if it is partial, then obviously you need to go by EM algorithm, right? As we do in the earlier cases, because then you cannot directly compute such things then you need to have, since you cannot directly compute such things, you need to go with MLE, maximizing the outcomes of this, this, and this with respect to these three, right? That's what we do in expectation maximization.
Yes, sir.
Yeah. So this I mean, this is out of our scope. I mean, we just if you need some problem to solve in this way in your domain, irrespective of what you are doing next. So you may think of using expectation maximization algorithm here also in hidden Markov model to predict, to find the hindsight, to monitor the most likely explanation and everything. Okay. So in textbooks, usually what you will find mostly is just the explanation of the algorithms. But if you can understand these steps, it's basically we just formulated the algorithms via these steps. Like in textbook, you will see the forward algorithm that's directly given, Viterbi algorithm. Viterbi algorithm is not so much fancy to be looked upon, because it is just our derivation followed up in the maximization, which is a dynamic program. That's it. I mean, there is no such very much awesome factor of Viterbi. Yes, Viterbi first noticed it and solved it, but it's a practical derivation from the probability computations using marginals, conditional independence, and the priors. Okay, so here I stop with the hidden Markov thing. Any questions I can answer? Okay, so let me then stop recording.